identify what are the limitations. Why cannot we simply use magnetic circuit to design motors? Why we need those sophisticated finite element analysis? Okay. All are familiar with B and H, right? Is there anyone who doesn't recall B and H? Okay, so B is the flux density, H is the flux intensity. And the relation is B is equal to mu H. Mu is called permeability, and permeability is equal to permeability of air or vacuum, mu naught, which is a constant, and mu r is the relative permeability. Okay, so if we simply look at this equation, we may think that B and H is linear, but it's not for electrical steel. Okay, there is a non-linearity. The next one is flux. We should remember the B flux density, if you multiply it by the cross-sectional area through which the flux is passing, gives you the flux. And flux, we can also actually, it's actually the definition of flux is coming from the your first postulate of magnetic field, that is the div or diversion of flux B is 0, if someone recalls. What does that physically mean is that a piece of magnet, if you cut it, you can never separate north and south pole, right? North and south pole always exist together. Even if you cut it, a new north and south pole will appear there. Okay, so that is mathematically becomes that magnetic flux or magnetic flux density. It's doesn't divert away. It's only which is the mathematical form is div of B is 0. Okay, that's the differential form of the to express that. And that also leads us to that in a closed total flux in a magnetic circuit must be always 0, like the current, right? Kirchhoff's current law. Similarly, we have this first postulate is actually kind of Kirchhoff's law of the magnetic flux. Total flux in the magnetic circuit always must be 0. And the other important component is magnetic vector potential, and this comes very much from the your relation vector relation of the first postulate, that is div of B is 0. So according to vector calculus, if div of a vector is 0, then that same vector can also be expressed as a curl of another vector. Okay, so that another vector in case of magnetic field is here, as you can see, this A. This A is known as vector magnetic potential. And we should remember that magnetic vector potential is not unlike the electric potential. Electric potential you can measure, which is your voltage, right? But magnetic potential we cannot measure. It's actually a mathematical term. It's not physically, it doesn't physically exist, okay? But it helps us actually to solve magnetic density and develop a equation, differential equation, to do the calculations such as finite element analysis. Okay, so B, the flux density, is that means can be expressed as a curl of the magnetic vector potential, and we can, if we know magnetic vector potential, we can directly find also flux. So flux is kind of like current, and magnetic potential is kind of like voltage for magnetic circuits. And another thing is that using the magnetic vector potential, we can find a second order differential equation known as vector Poisson's equation. So that this is Laplacian. This del square is known as Laplacians. The Laplacians of magnetic vector is equal to permeability times current density. Negative of permeability, because this is again coming from fundamental magnetics, electromagnetics. And this is actually a second order differential equation, okay? In fact, all the finite element analysis that we talk about, they try to solve this equation at the back, okay, which we don't see. Those who use finite elements, you only see the geometry and you just see how they have solved the flux density, etc. But in the back side, actually, it is trying to solve this equation. Okay, it could be three-dimensional equation. A could be function of x, y, z. So it's a three-dimensional second-order differential equation, and you have to solve it using numerical methods such as finite element. Okay, and then the other equations are Maxwell's equations. Okay, that the four Maxwell's equations. First one is actually related to electrostatic. Second one is magnetics. Third one is also magnetics. And the last one actually relates electrostatic with the magnetics to give us electromagnetics. Okay? And these four equations again are the base of many finite element analysis. Okay? Together with Poisson's equation, that's what they solve. Okay, finite element and software packages, these are the equations they solve. We may discuss a bit more later, but just today we are reminding you that these basic equations. And then this is basically telling you or reminding us why the electrical steel has non-linear characteristic. Okay, if we simply look at B equal to mu H, it appears like mu is a constant, so B equal to mu H should have been linear. Why in electric steel we have this non-linear part? So it comes from the saturation, right? Magnetic saturation. What does the magnetic saturation means? We'll refer to them a lot later. So what does magnetic saturation actually means is that in the, let's say the case of iron or electric steel, you have dipoles, magnetic dipoles. And these magnetic dipoles are one region of the material. The magnetic dipoles are aligned in a particular direction, okay? But this direction are usually random. So there is no net magnetic dipoles. But if you magnetize it, electrical steel, all the dipoles align into one direction. And when they are all aligned, then we say it is saturated. The material is magnetically saturated. And even if we keep increasing H when they are saturated, we do not get any more higher magnetic flux density. Okay, so that's the saturation. And usually we can use Ampere's law, basic Ampere's law, to calculate flux using magnetic circuit. In fact, magnetic circuit is coming from this Ampere's law. Okay, and so the basic law is line integral of H, closed line integral of H is equal to number of turns times current. So if we consider this very simple magnetic circuit, we have a ring, iron ring, and let's say we have a coil here, and current is passing through this coil. So, and it has n number of turns in this coil. And when the current passes through this coil, it is going to induce magnetic flux. And this magnetic flux, if this ring is iron ring, then the flux should be flowing in this ring. Okay? So this circuit we can write taking help of Ampere's law. So line integral of H time L. So L is in this case this closed path, closed flux path. So it's a circle, in our case 2 pi r simply. Okay, if the radius, mean radius of this ring is r, then LC or length, core length is 2 pi r simply, equal to number of turns time current. So this Ni is known as MMF, magnetomotive force, which forces the flux to pass through. And from there we can, if we express this in terms of flux, then flux becomes equal to mu Ni S. S is the cross-sectional area of the ring, Lc is the length, and mu is the permeability. So this, in this expression, S over Lc time mu, this part, can be, it's kind of like a resistance. If you recall, a resistance of a coil, a resistance of a wire is length over surface area times the resistivity, right? In case of magnetic circuit, it is again length over cross-sectional area but times over permeability, mu. And this component is called reluctance, okay? So the ring that we have here, we can write it like a circuit, or we can draw like a circuit. So in this circuit, this reluctance is like our resistance. Ni is like your voltage, which is the MMF in case of magnetic circuit. And what is flowing through it is the flux. So any magnetic device, including motor, in fact, we can use this reluctance MMF and can draw like a circuit and can calculate flux analytically, okay, and which is known as magnetic equivalent circuit. Can you see any issue? What is the limitation of this type of problem? Like, why we cannot always use magnetic circuit? What's the problem? To calculate reluctance, what's the problem? Why cannot we calculate reluctance always for everything, every magnetic devices? To calculate reluctance, I need to know the length of the close length of the flux path, Lc. I need to know the cross-sectional area, S, and I need to know the permeability. So let's say I have a motor. I know the geometry, so I know what is cross-sectional area. I know Lc, but I may not know accurately permeability, okay? Because your permeability is not constant. When it is saturating, permeability is no longer constant, right? Permeability constant only here in the linear region. So if mu may not be, you may not be able to estimate mu accurately, because the most of the time motors will have magnetic saturation, okay? So that's why if we use magnetic circuit to find flux in a motor, it will always overestimate because it ignores saturation, okay? And the other problem is the leakage and the fringing. So in the motor, we always have an air gap between the stator and rotor. So when you have air gap, some flux may not cross the air gap, which is the leakage flux. Again, the estimation of leakage flux linearly is difficult. And also in the air gap, when we use Ampere's law, we assume that flux is perpendicular to the cross-sectional area through which it is passing. But in reality, they may not. At the edge of the gap, they could have fringing. So fringing means, again, the estimation may not be correct, okay? So in magnetic circuit, equivalent magnetic circuit method, you ignore fringing, you ignore leakage, you even ignore saturation. That's why this method, it may not give you accurate flux information, and almost always overestimate it. Okay. This is just some magnetic solutions. This is just, I will skip this. You can look at it with the slides later. So here is a motor equivalence, magnetic equivalent circuit, how you can draw them. It's not that you can't, you can draw it. So in your left hand side, you can see a surface type permanent magnet motor. In your right hand side, you are seeing a interior type permanent magnet motor. And here they're attempting to draw the equivalent circuit by drawing the reluctance, okay, various reluctance of various parts, okay, and trying to calculate the flux. So it's possible that you can do it for a rough estimation in your as an initial design, but you must know the geometry properly to calculate the reluctance. You must know the materials property to know the permeability mu, and then you can use the equivalent circuit also to calculate or to estimate information of a motor. Okay? I think that finishes our today's talk. Tomorrow we will be looking at actually design. Okay? Is there any question up to here? Key points? Any key points that you think important to remember from here? I will suggest to recall the reluctance. Okay? Thinking about the leakage and recalling the saturation. Okay? These terms will appear again when we discuss design. So the fundamental about these terms, if you're clear, then it's easy to understand the more advanced part of the design problems. Okay? Okay, I think we'll stop here. Sorry? Yes? So BLDC and PMSM motors are actually magnetically same. Okay, so this surface type motor, which we'll be talking about maybe tomorrow. So this is called surface type. The magnets are glued on the surface of the rotor. So this motor, for BLDC, this is the rotor they use, and the stator could have concentrated type windings, okay, and they produces usually trapezoidal back EMF, and mostly the control of BLDC and PMSM is different. So in PMSM, you will use a more advanced control like field-oriented control or something. But in BLDC, usually it is more like much more simple control. So it could be done through the lookup table-based system. Okay, and you produce a square wave from it, the inverter. Whereas in the PMSM, it's sinusoidal back current waveform you try to produce. So that's the difference. But the problem with BLDC is that you will, because you have square waveform, current square waveform, your torque is not smooth. Torque will have a lot of ripples. So if you try to use that in a car, electric car, you could have not smooth run, right? There will be a lot of vibration, noise, etc. So BLDC is very good for small power applications. Like nowadays, nearly all small motors even in your computer fan, this, if you try to look at your laptop fan, it's a BLDC motor. So all small motors are BLDC nowadays, but not for large applications like traction because of that torque ripple issue. Yeah. Any other question? Yes, please. Yes, so when your rotor is rotating, so the magnetic circuit only can look for only particular position, right? If rotor changes, if the rotor is rotating, it cannot account for the rotation. Okay, so the equivalent circuit, magnetic equivalent circuit is good, similar to magnetostatic analysis in finite element, where your rotor you consider only for a particular rotor position. If you want to see what's happened in a different rotor position, you have to redraw the whole circuit, okay? So not very good to account for rotation equivalent circuit. Okay? Yes. Displacement current in the, usually for, you mean the Maxwell's displacement current, right? So these motors, especially motors type electromagnetic applications, the frequency is relatively low, right? We only make maximum, even if we take the high speed motors, the frequency is only a few kilohertz. Okay, so at such low frequency, displacement current in the main performance, no effect at all. So you consider the electromagnetic as a field, not as a wave. Okay, but if we go for very high frequency power electronics, such as the silicon carbide or the this GaN type converter or inverters, where your switching frequency could be 100 of kilohertz, even they're talking about megahertz. So if you have such high switching frequency, then your the harmonics produced by the PWM could be in up to very high megahertz. Then they start to behave, those harmonics may start to behave like a wave, okay, magnetic wave. And then maybe displacement current could have some effect, especially in your cable, in your insulation, etc. Because the displacement current is more about your insulation property. It can affect the insulation property of the cables, conductors, etc. through this partial PD, right? So those type of effect can become severe. But for conventional motors or even up to few kilohertz, it is can be ignored. Okay, all good. I hope you have liked it, and I will hope to see you tomorrow with more information or more discussion on the design, exact actual PMSM. Okay, yeah, thank you. Just on time.
Yeah, next session will start by 2:15. Okay.